Now example 7.15. A cord of negligible mass is wound round the rim of a flywheel of mass 20 kg and radius 20 centimeter. A steady pull of 25 Newton is applied on the cord as shown in figure. The flywheel is mounted on a horizontal axle with frictionless bearings. A. Compute the angular acceleration of the wheel. B. Find the work done by the pull when 2 meters of the cord is unwound. C. Find also the kinetic energy of the wheel at this point. Assume that the wheel starts from rest. And D. Compare answers to parts B and C. Now see, this one is the flywheel. Flywheel is after all a disc. Which one is fixed with this axle passing through the center. Okay. And now a cord is wounded on it, and now at the free end of the cord 25 Newton constant force is applied. Okay. Now first of all we have to calculate the angular acceleration. Now see here, mass of the disc means flywheel, that is given to you 20 kilogram, and radius that is 20 centimeter, so 0.2 meter. This much information is there. So first of all, calculate moment of inertia of this disc. We have the equation of moment of inertia of the disc, that is half mr square. So half into 20 into 0.2 square, we will get moment of inertia, that is 0.4 kilogram into meter square. Now we discussed torque tau, that is equal to I alpha. This equation we derived. And as per definition, torque, that is force into perpendicular distance from the reference point. So force, that is F, and this perpendicular distance is the radius of the disc. So we can write torque tau, that is R into F also. So here now make alpha as a subject. So alpha, that is RF upon I, substitute the values. R, that is 0.2, F, that is 25, and I, that is 0.4. Solve this one, you will get alpha. Then after work done, when this string unwound by 2 meter, it implies that when it unwound by 2 meter, it implies that the displacement of the string in downward direction, that is 2 meter. And the force in downward direction, that is 25. Both are in the same direction. So W, that is F into D. So W, that is 50 joule. Then after, during this rotation for 2 meter unwound of the string, okay, we want to calculate the kinetic energy. Now kinetic energy, that is half I omega square, but we don't have omega. I that we calculated. Now see, initial angular speed is 0. Omega, that is how much that we want to find. So we can use the equation omega square minus omega 0 square equal to 2 alpha theta. Omega 0 is 0, so omega square equal to 2 alpha theta. But what is theta? Now see here, theta, that we can write length of unwound string upon radius of the wheel. How we can write this? See, here it is represented. Suppose this red point here, this point, reaches at this position. So at that time, we can say the string equal to this length of arc that will unwound. Now arc, that is angle into radius. So angle, that is arc upon radius. But arc, that is exactly equal to unwound string. So we can write theta equal to length of unwound string upon radius of the wheel. Length of unwound string that we have to take 2 divided by radius of the wheel 0.2, you will get theta. And if you substitute the value of theta and alpha here, you will get omega square. And then you can calculate omega. Now, directly substitute this value of omega square in the equation. Rotational kinetic energy, that is half I omega square. Your I, that is 0.4, we already calculated here. Omega square, here we calculated, substitute. You will get rotational kinetic energy. And now you can observe this thing. Your rotational kinetic energy and work done, both will come to same one. Clear to all of you?